Okay, we're going to do our next example now, the one that needs to be worked out on paper. And this is the example of two people sitting on a teeter-totter. And we're going to do the example first of two Shannons sitting on the teeter-totter. We always like to draw our free body diagram. So here's our teeter-totter. We know there has to be something that stops the teeter-totter from going down into the center of the earth. We've all been on teeter-totters and we know that there's something that it sits on. But that thing can't stop it from twisting or rotating. We can't stop that degree of freedom. We only have the ability to stop it going up and down, and probably to stop it from going in that direction as well. So that is our reaction in the y direction. We know that we have two loads acting on this. This is two Shannons sitting on this teeter-totter. Shannon weighs the same in both of these, but we have a point load from Shannon 1, and we have a point load from Shannon 2. And both of these are 0.8 meters from the point where the teeter-totter is supported. We've been told that Shannon 1 weighs 0.65 kilonewtons, which is also equal to Shannon 2. We know that a force with eccentricity is the same thing as a force directly through the centroid and a moment. So if we wanted, we could redraw this free body diagram. We have our teeter-totter. We have our reaction y. For this to be in equilibrium, the sum of everything in all the directions has to be 0. We know that this is the same as PS Shannon 1, PS Shannon 2, and the moment from Shannon 1 and the moment from Shannon 2. Intuitively, you understand that this is a balanced condition. If you put two weights the same distance apart on a teeter-totter, you know it's going to be in equilibrium. But it's going to get harder to just know that off the cuff. So we're going to do the calculation to prove this so that we can see how to do it when it gets more complex. We know that moment is a force times its eccentricity. So the moment for Shannon 1 is the force from Shannon 1 times the eccentricity of Shannon 1. And we know that the moment from Shannon 2 equals the force from Shannon 2 times the eccentricity of Shannon 2. We want to make sure that everything is in equilibrium. We want to be sure that the sum of the forces in the x direction, in a world where that's positive, we want to make sure that that equals 0. To be in equilibrium, all of our degrees of freedom need to equal 0. Well, it doesn't look like we have any forces acting in the x direction, so 0 does equal 0. That's in equilibrium. Well, let's see if the forces in the y direction are in 0. So everything going upwards is in the y direction. We have Shannon 2, Shannon 1, and some unknown reaction. We don't know what the value of that reaction is, but we want this thing to be in equilibrium. So we need to know what our y needs to be for this to be in equilibrium. We have PS Shannon 2 going downward. We have PS Shannon 2 going downwards, so it's negative. We have PS Shannon 1 going downwards, so it's negative. And then we have RY going upwards, so it's positive. And we want to know if this is in equilibrium. We want all of this to be in equilibrium. Well, these are values we know. We know that this is minus 0.65 minus 0.65 plus our unknown ry. We want to know what ry needs to be to make this equation true. So that means we can set ry to everything else to see what makes this true. Essentially, we're going to rearrange this equation. So we can rearrange this, and we rearrange this, we get ry equals 1.3 kilonewtons. So for this to be in equilibrium, ry needs to be 1.3 kilonewtons. We also have one more equation to solve, and that's the moment about our point zero. We're right here, this spot we're trying to spin everything about. And we're gonna say anything spinning in that direction is positive. So anything that tries to make our paper spin in this direction, if we put a thumbtack right here and I tried to spin this paper, anything spinning it in that direction is positive. Anything that spins it in this direction is going to be negative. Well, we're talking about spinning things about this point. That goes right through it. To be a moment, you need a force and an eccentricity. So that doesn't make it spin, that doesn't make it spin, and that doesn't make it spin relative to that point. We do have two moments that are trying to make it spin. We have the moment due to Shannon in this direction, which is positive because it's trying to make it spin. Look, you can see our arrow is in the same direction, and that's our positive direction. MS2 is going in the opposite direction, or the negative direction. And we want this to be zero. We need to know if this is in equilibrium. We know that MS1 is PS1 times ES1, or 0.65 times 0.8 minus 0.65 times 0.8. MS1 minus MS2 equals 0. If we plug that in, 0 equals 0. This is in equilibrium. So we have a system that works. So now let's take a look at this where Dave replaces Shannon. So we have the same system. We have the same teeter-totter. We have our reaction Y, and we have Shannon sitting here, and she is 0.8 away. And we have Dave sitting here, and he's also 0.8 away. Now, they have told us how much both Dave and Shannon weigh. Shannon still weighs 0.65 kilonewtons, and Dave weighs 0.85 kilonewtons. So intuitively, if you've been on a teeter-totter and both people are sitting the same distance apart from the centroid, you know that the heavier person is going to sink down to the ground, or that this teeter-totter is going to try to swing in the negative direction. Remember, everything this way, everything going this way is what we call positive, and everything going this way is what we call negative. So Dave, we're gonna mathematically prove that Dave is trying to make this teeter-totter spin in the negative direction. We have a reaction here that we don't know what it is, but there's nothing that can stop rotation here. So we could, if we wanted, redraw this diagram. We can redraw this to look like PS and PDs, and the moment from Shannon, and the moment from Dave. We can go through and start to do this calculation. I'm going to start to jump some of these steps because we're going to start to get pretty fast at this. So the sum of the forces in the x direction, we want to be 0. Well, there are no forces in the x direction, so 0 equals 0. We can sum the forces in the y direction, and we want this to be 0. Well, we've got Dave going downwards and Shannon going downwards, and our RY1 going upwards. And we want this to be equal to 0. We're trying to see if that's 0. Well, we know the value for Dave is minus 0.85, and Shannon is minus 0.65. And we don't know what R1 is. We can see what it takes. What does R1 have to be to make sure this doesn't sink into the center of the Earth? And RY needs to be 1.5 kilonewtons. It makes sense. With two Shannons on it, for this to be in equilibrium, this teeter-totter needs to push back with 1.3 kilonewtons. With Dave and Shannon on it, it needs to be 1.5. If we needed to look at this teeter-totter in a whole bunch of situations, we'd know that Shannon and Shannon would be 1.3, Dave and Shannon would be 1.5, so it looks like the worst case there would be 1.5 kilonewtons. That's talking about another step, but I just want to kind of keep that in the back of our head. Let's now also sum the moments about this point right here. Everything spinning in that direction is a positive, and we want to know if this is in equilibrium. And if we have any unknowns, what it would take for this to remain in equilibrium. So we have the moment due to Shannon in the positive direction, and the moment due to Dave in the negative direction. The weight of Shannon and the weight of Dave and the weight and the reaction all go through the centroid. Now people are probably saying, wait, no, those were over here. Except we know that a force through the centroid and a moment about the centroid is the same thing as a force some distance from the centroid. We're gonna soon start not drawing that diagram. We'd look at everything going up and down, and we'd look at everything going side to side, and we'd say, okay, our moment, we're not gonna take the step to write our moment. We're gonna jump right to this Shannon causes a moment of this spinning in this direction, and that moment is the weight of Shannon times its eccentricity. And then Dave is spinning it in the negative direction, so the weight of Dave times Dave's eccentricity. The weight of Shannon is 0.65, and she is 0.8 meters away. The weight of Dave is 0.85, and he is 0.8 meters away. If we sum this up, we get minus 0.16 kilonewton meters equals 0, not in equilibrium. And look, minus 0.16 kilonewton meters, so a moment of minus 0.16. Negative means it's trying to spin in this direction. So sure enough, that's the negative direction that we anticipated Dave would try to spin this teeter-totter. I'm going to go on and do the next part of this, which is where would Dave need to sit, or where would we need to adjust Dave to be to keep this in equilibrium? So we're going to do the same teeter-totter scenario. We have our reaction Y. We have our point load from Shannon, and Shannon is 0.8 meters away. And we have our point load from Dave. And we do not know what Dave's eccentricity is, or we want to know where Dave needs to sit to make this be in equilibrium. Now, intuitively, if Dave is trying to spin it in that direction, where do you think he would go? Would he scooch forward, or would he scooch backwards? I think that Dave would move forward to try to balance this system out. If you've ever been on a teeter-totter, you know that you can adjust your position to change how much you try to spin your teeter-totter. So we know that the point load of Shannon is 0.65 kilonewtons, and the point load of Dave is 0.85 kilonewtons. And we want to know what it takes for this not to spin. So I'm not even going to redraw these as their moments and the load over here. We're going to jump right into summing the forces in the x direction. We don't have any, so 0 equals 0. That works out well. Sum of the forces in the y direction, where everything going upwards is positive. Our Ry is going upwards, and we've got our Shannon going downwards, and our Dave going downwards. We know what the values of Shannon's and Dave's weights are. Ry equal, we could rearrange this if we wanted. So to be in equilibrium, Ry is 0.65 plus 0.85. You can see that I rearranged the equation. I brought these over to the other side, which means we change their symbol. So Ry for Dave and Shannon to be in equilibrium still needs to be 1.5 kilonewtons. The total weight pushing down hasn't changed. Now, let's sum the moments about this point right here. We have Shannon trying to spin the teeter-totter in this direction, which is a positive direction, and a moment is a force times an eccentricity. So we have the point load of Shannon times the eccentricity of Shannon. We have Dave trying to spin it in the opposite direction, or in the negative direction. And we know we need the point load of Dave times the eccentricity of Dave, because to be a moment, you need a force times an eccentricity. Our Y tries to pass right through the point, or its eccentricity is 0. So force times 0 would be 0. And we want to know if this is an equilibrium, or we want to know what it takes to be in equilibrium. So we're setting this equation to 0. We know the force of Shannon is 0.65, and we know the eccentricity of Shannon is 0.8. We know the weight of Dave is 0.85, but we don't know the eccentricity of Dave. That's what we want to find out. We want to know what the eccentricity of Dave needs to be for this equation to be in equilibrium. We can rearrange this equation. The eccentricity of Dave for this to be in equilibrium needs to be, we would bring this over, 0.85 divided by, actually, sorry, you can rearrange this a few ways. We would bring, this is probably an easier way to write it. So this is a negative here. We have minus ED equals 0.6 minus 0.65 times 0.8 divided by our 0.85. But a negative and a negative is the same thing as the positive of that. So ED equals 0.65 times 0.8 divided by 0.85. ED, or the eccentricity of Dave, for this to be in equilibrium, needs to be 0.6117 meters. So Dave would need to shift forward to be 0.6117 meters away for this to be in equilibrium. Let's try this again, but let's conceptually talk about it, that instead of spinning about this point, to be in equilibrium, It means it's not moving. It means it's not moving anywhere. The point we're spinning about, it's easy to talk about it in a teeter-totter because we know it's actually that point it wants to spin about. But if it can't spin about that point or that point. So let's talk about this exact same problem, but imagine spinning this about Shannon's butt. So we're going to do this again, but the point we're going to spin about is Shannon instead. So we have our reaction. We have the point load due to Shannon. We know Shannon is 0.8 away from that point, and we have the point load due to Dave, and we want to know how far away Dave is here. So let's just call that X. But let's use this point as the point we spin about in the world. We can pick it. If it's not moving, it's not moving. Conceptually, it's not spinning about that point either. Intuitively, you know it's not spinning about that point. But if it's not, we should be able to mathematically prove it or see what it takes for this whole system not to spin about Shannon's bum either. So let's take a look at this now. Let's sum our forces in the X direction. 0 equals 0. There's no forces going in the X direction. Let's sum our forces in the Y direction. We have minus the point load from Shannon, minus the point load from Dave, plus the unknown reaction. We can rearrange this and we get that Ry equals 0.65 plus 0.85 equals 1.5 kilonewtons. So no matter what, we still have that same upwards reaction. Now let's do this one. Let's sum the moments about Shannon instead. We're still saying anything spinning in this direction is positive and anything spinning in that direction is negative. But now we're going to imagine we have a thumbtack right here and we're trying to spin the paper around it. Well, Shannon now passes directly through that point. So Shannon doesn't cause it to spin at all about Shannon. She tries to make it spin about that point, but not about Shannon. So Shannon has no contributing moment to analyzing it about this point. Ry, if we put a thumbtack here, does try to spin it. Look, you push up like that, it's going to try to spin the system in that direction. So we try to spin it in that direction. That's our positive direction. So we've got positive Ry, and the distance Ry is from Shannon is 0.8. Now the hard one, Dave. Dave is trying to spin the teeter-totter about Shannon, but he's trying to spin it in that direction. So we've got minus the point load due to Dave, and we need to know what eccentricity Dave is. Well, look at this. He's this far away from Shannon, which is 0.8 plus x. We don't know what x is. We want to know what x needs to be for this system not to spin. So we have 0.8 Ry minus, and the point load from Dave is 0.85 times 0.8 plus x equals 0. So 0.8 Ry, I don't have it worked out exactly this way in the calculation. In this one, I assumed we had all the unknowns and we were confirming it's an equilibrium, but I think this might be a slightly better way to work it out. So minus 0.85 times 0.8 is minus 0.68, and then minus 0.85 times x is minus 0.85x equals 0. Our 0.8 times Ry. Well, we know what Ry is. 0.8 times 1.5 minus 0.68 minus 0.85x equals 0. 0.8 times 1.5 equals 1.2 minus 0.68 minus 0.85x equals, well, actually, let's bring that over to the other side. So it's 0.85x. 1.2 minus 0.68 equals 0.52 equals 0.85x. X equals 0.52 divided by 0.85, or 0.61176 meters. So this distance, it didn't matter what imaginary point we picked to sum this about, as long as we were saying we needed to figure out what it took for B in equilibrium, we can pick whatever point we want. We know it's trying to spin about that point, but technically it's trying to spin about every point. We just understand that that's not where it's going to spin. So to be in equilibrium, it's not spinning about that point either. So we know that we can calculate it no matter what, and it doesn't matter what spot we look at.